Swayam Prabha. Digital India. Educated India.
So our next speaker is Dingao Lee. The title of the presentation is Synthesis of Heat Exchanger Network with Complex Phase Transition Based on Pinch Technology and Carbon Tax.
For all members of the teachers feel good. I'm from the College of Chemical Engineering, Beijing University of Chemical Technology. The title of my paper for today's conference report is Synthesis of Heat Exchange Network with a Complex Phase Transition Based on Pinch Technology and Carbon Tax. The faculty advisors of the paper are Professor Sun Wei and Senior Engineer Wang Jingde. This report is divided into the following three parts. The first part is study background and significance. First, research background. Now, the reduction of carbon emission becomes a mission to every individual and enterprise. Even though more popular research topic under this category is carbon capture and storage, the renovation in existing facility is still the fundamental solution. The next is study significance. Energy is an important foundation for national economic development. In addition to realizing the transformation of the energy structure, energy saving is also essential at this stage. The optimization and transformation of the heat exchange network is of great significance for the energy saving and the emission reduction of the chemical process industry. At present, the optimization of heat exchange network is mainly divided into the following four methods. The first is pinch technology. The second is mathematical planning method. The third is hybrid method. The last is artificial intelligence method. In the late 1970s, the pinch technique possessed by Linghoff began to develop and took an important place in energy-saving applications. The emergence of pinch point technology provides a systematic approach to energy conservation in the process industry. Features of pinch technology is divided into the following three parts. The optimization goals of the heat exchange network are generally as follows. Total annual cost, environmental impact, system reliability, engineering consumption, carbon emissions, and retrofit engineering quantity. Carbon tax, as a tax policy aiming to quantify the cost of carbon emissions for enterprise, has been carried out in some countries. To reduce total annual costs for enterprise, it is necessary to integrate carbon tax into the unit cost function of heat exchange network synthesis. At present, most study on heat exchange network is assumed no phase transition in streams. However, streams may undergo phase transition during heat exchange in real process, and the latent heat of phase transition has a great influence on the whole heat exchange network structure, which requires a proper consideration. According to the actual situation, the heat exchange system can be divided into three categories. The following four temperature enthalpy diagrams correspond to the temperature and enthalpy changes of the streams in the three heat exchange systems during the heat exchange process. Taking the last picture as an example, the phase transition in mixture streams is considered in certain streams, which makes the temperature vary during phase changing process. Therefore, in this paper, considering the complex phase transition stream and the cost of carbon emission, the synthesis of heat exchange network is carried out based on the pinch point technology. The next part is the heat exchange network synthesis analysis. In this work, the synthesis of heat exchange network is performed on a NASA cracking unit in China. 8 mixture streams from cracking gas variation cycle and deprofanizer powers are selected due to their large energy demand and room for energy optimization. Specifically, 4 hot and 2 cold streams of them undergo phase transition during heat exchange according to the requirement of process. To better describe the process in heat exchange network, a soot stream is defined, which can be characterized by a constant heat capacity with component transferred from one phase to another in one stream, usually between gas and liquid phases. 6 streams are considered in different temperature intervals according to their phase change characters. Taking each one stream as an example, it is a vapor-liquid coexistence phase after heat transfer. According to the property of different components in the mixture stream and the enthalpy changes, its phase transition is divided into heavy hydrocarbon phase transition part and water phase transition part. Similarly, C4 stream is divided into liquid phase part and phase transition part. Similarly, the rest streams with phase transition are divided in the same way. Besides, the heat capacity flow rates of the 2 cold streams without phase transition are treated approximately as constants. Temperature interval and the corresponding heat capacity flow rates for all streams are shown in Table 3. As a heat exchange network consists of multiple streams and phase transition, the pinch point is hard to specify by horizontally moving temperature enthalpy curve in enthalpy diagram. Problem table method is therefore adopted to obtain the pinch points, where the moment of cold and hot utilities can be calculated more accurately. Different choices of the suitable minimum approach temperature will affect both utility cost and equipment investment. According to precise knowledge and stream characteristics, the suitable minimum approach temperature of the heat exchange network is calculated from 5 to 14 degrees Celsius. As an example, the calculation of the problem table method with a suitable minimal approach temperature equal to 8 degrees Celsius is illustrated as follows. The calculated temperature interval is shown in Table 4. After the calculation of enthalpy balance in each temperature interval, the pinch point temperature, minimum hot utility, and cold utility can be obtained. Compared with the actual hot and cold utilities of the original heat exchange network, it can be calculated that the energy saving potential reaches 47.9% and 27.1% respectively. Consistent with the above calculation, the results with the different suitable minimum approach temperature are obtained as shown in Table 5. The optimal, the suitable minimum approach temperature of heat exchange network is obtained by the evaluation based on total cost. First, the capital cost of the heat exchange network, including the manufacturing expenses of a heat exchanger area and the fixed charge of a heat exchanger. In this paper, the manufacturing cost of heat exchanger area is assumed to account for 94% of the investment costs, and the area of a heat exchanger is calculated as follows. Second, the objective function of utility cost, including consumption costs of heat utility and cold utility. So the total annual cost generally consists of two parts, investment cost and utility cost. In order to reduce the energy consumption of utility, heat exchange network needs to be improved to recover the effective energy between the streams. The total annual cost of the heat exchange network is determined by a trade-off between the operation cost and the investment cost as shown in Table 6. As shown in Figure 5, the lowest total annual cost obtained with a suitable minimal approach temperature equal to 9 degrees Celsius, compared with the total annual cost of the original heat exchange network. The saving potential of optimized heat exchange system is 25.18%. Energy loss is closely related to carbon emissions, and the increasing amount of heat required from the heat exchange network will reduce the amount of additional hot utilities required, which will result in lower carbon emissions. To reduce carbon emission cost based on carbon tax is introduced to the total annual cost objective function, and the carbon tax calculated by multiplying the annual carbon emissions by the carbon tax price as follows. The calculation of the heat load supplied to the system with fuel is simplified as follows. The related cost parameters are shown in table. The calculated results of cost with consideration of carbon emission are shown in Table 7. Figure 6 shows the total annual cost graph obtained by pinch point method after introducing the carbon emission target, and its optimal, the suitable minimal approach temperature is 8 degrees Celsius. The annual carbon emission of the heat exchange network obtained after introducing the carbon emission target is 4.42% lower than the heat exchange network obtained by the traditional pinch point method, and the corresponding annual carbon emission can be reduced by 4,816.56 tons. Meanwhile, the total annual cost is 0.56% lower. Finally, the optimal, the suitable minimal approach temperature of heat exchange network is selected as 8 degrees Celsius, which can reduce the annual carbon emission by 47.9% to 96,689.31 tons compared with the initial heat exchange network. And the total annual cost is reduced by 31.32%. The kick-off method is employed for the matching among streams to obtain the energy optimal heat exchange network of the process as shown in figure. The last part is the research conclusions. aiming to an ethylene plant cracking gas separation unit. Carbon emission target is introduced to the synthesis of heat exchange network with complex phase transition process, and the total annual cost under the carbon emission target is evaluated. Compared with the traditional pinch pump method, the optimized heat exchange network is more energy efficient, with lower carbon emission and less annual cost. Compared with the initial network, the heat recovery volume increased to 25,778.9 kilowatt. The annual carbon emission is reduced by 96,689.31 tons, and the total annual cost is reduced by 4,464,559 US dollars a year. Thanks for your attention, and be happy to answer your questions.
So I don't think the speaker is available online. Let's thank the speaker. Is he available? Okay, all right. So let's move to the third speaker. So our third speaker is Dan Lee, and he is going to present on novel multiple grid formulation for scheduling of multipurpose batch plants with indirect and direct material transfer schemes.
I think I need to first share my screen.
All right.
Okay, can you see my screen now?
Yes.
Okay, yeah, can you start?
Please go ahead.
Okay.
All right.
Yeah, first, thanks for the introduction of the chair. I'm very honored to give such a talk today. I'm Dan Lee from the Central for Process Integration at the University of Manchester. My work is about the novel multiple time grid formulation for scheduling of multipurpose bench plants with indirect and direct material transfer schemes. The work is introduced in the following 4 parts: introduction, mathematical formulation, computational studies, and conclusion. We first need to know what's scheduling in the manufacturing. Scheduling is the process of arranging, controlling, and optimizing work and the workloads in a production process. Before scheduling, 3 kinds of information would be given: the production processes, resources, and customer requirements. Here, the resources include the manpower, storage, utilities, unit, and so on. And the customer makes a production request to the manufacturer or give a due date. Now we can generate a scheduling solution to satisfy the customer requirement and optimize our objectives. So the scheduling is a decision-making tool, and effective, efficient scheduling can be a competitive advantage. In this work, our scheduling object is the multipurpose bench plants. The multipurpose means the units designed to perform multiple tasks. Several products in the plant are manufactured through product-specific processing steps. Bench mixing, splitting, and recycling are permitted in this kind of plants. So basically, solving the scheduling problem of the multipurpose bench plants means to determine the benching, including the bench number and the bench size of tasks, and assignment of units and the sequence of tasks to satisfy the customer demands. The most commonly used method for the scheduling of multipurpose bench plants is the unit-specific event-based mathematical formulation. In this kind of formulation, the scheduling horizon is divided using the event points. And the unit-specific means the start time for one event point on different unit can be various. For one state, the consumption task should start at the next event point or later if the related production task finish at the event point N. This figure shows a scheduling example. Here, the task I1 and I2 are the production and the consumption tasks respectively. And the I2 must start after the event point N2 because the corresponding production task I1 is performed at the first event. And in the mathematical formulation, there are binary and continuous variables. The binary variables denote the assignment of unit and the mapping relations between the tasks and the event points. And the continuous variable denotes the batch size, the start time and the end time of tasks. In most existing models, the unconditional sequencing is enforced for related tasks without monitoring the actual material flows. This can be reflected by the sequence constraints in the literature work. For different tasks, producing and consuming the same state, the start time of the consumption task at the next event point must be larger than the finish of the production task at the event point N. In the right-hand example, this constraint handles that the task T2 must start after the task T1 on both unit J1 and unit J2, even though the T2 didn't use the material from the unit J1. If we can relax the unconditional sequencing, the start time of task T2 can be advanced. In this way, the optimal solution of mixed span is reduced. So the unconditional sequencing in current models lead to the suboptimality or unnecessary event point. In this work, we use the rigorous conditional sequencing. It means the production and the consumption tasks are sequenced rigorously by accurately monitoring the material flow between the related tasks. There are two cases. In the first case, if the consumption task uses material from a corresponding production task, the sequencing relation should be like the start time of the consumption task should be larger than the finish of the production. This can ensure the sufficient material supply. And in the second case, if the storage can store material from the production, the finish time of the production task should be smaller than the consumption. This can ensure the storage inventory not to exceed the maximum storage capacity. In addition, in current models, material produced by one production must leave the processing unit at the end of the event point. There is a plan to produce the S3 within 8 hours. Using the existing models, the maximum production of S3 is 60 mass units. The state S2 produced by the task transferred to the storage or the downstream unit after production. Due to the maximum storage capacity of S2 is 10 mass units, the bench size of T1 should be 60. But its maximum bench size is 100. So the unit resources isn't fully used due to the limited storage capacity of state S2. For the same problem, we can manually get a better solution with the production of S3 is 100 mass unit. In this solution, the bench size of T1 can be 100 mass unit because we allow the processing bench partially transferred to the downstream unit, and the remaining material are temporarily held in the processing unit at the second event point. It means in this schedule, the unit G1 from 5 hour to the 6.5 hour provide additional sequence space for the state S2. From this example, we can know that allowing material to be temporarily held in the processing unit after production leads to better scheduling solutions. So in this work, we aim to develop a MILP formulation for scheduling multi-purpose bench plans using the unit-specific event-based modeling approach. There are three novelties of the work. The concepts of indirect and direct material transfer would be defined for the unit-specific event-based formulation. A bench is allowed to be temporarily held in the processing unit over multiple event points, and unconditional syncing between production and consumption tasks to avoid the real-time storage violation are modified. Next, I would introduce the mathematical formulation we have developed. There are 4 scenarios of material transfer. The MT1 and MT2 are transfer material into the storage from the unit after production. While in the MT3, if the storage capacity is large enough, the material from a unit can be first transferred to the storage and then transferred to the downstream processing unit. We define it as the indirect material transfer. And the MT4 is the direct material transfer. In this scenario, the remaining storage space is too small, so the material must be transferred directly to the downstream processing units. The definition of indirect and direct material transfer is to handle the sequencing relations between the related production and consumption tasks. The indirect material transfer between a production task and its corresponding consumption task is required when there is insufficient storage at the previous event point. These constraints express the total amount of a state consumed by the task at the event point. And should not exceed its inventory level at the previous event point, plus its amount through the indirect material transfer. Next, the direct material transfer between the related tasks are essential when there is no enough storage space to hold the material after production. As for the constraint by this equation, when the provided amount of one state plus its inventory level at the previous event exceeds the maximum storage capacity, the direct material transfer should be non-zero. All the material would be held in the processing unit. Okay, now we have already checked the material flow between the production and the consumption. If there are indirect material transfer between them, the variable Di would equal to 1. We would handle the consumption task on the unit G prime at the next event should start after the finish of the production at the event point N. And if there are direct material transfer between the related tasks, it means the ZD equal to 1. And the finish time of the unit G prime must be before the finish of the unit G at the previous event to avoid the overlapping on the unit G prime. As mentioned in the introduction, we allow the processing unit to store the material after production. Amounts of material stored in the processing unit should be smaller than the unit maximum capacity. And when one batch isn't held on the unit, that is the YS equal to 0, its corresponding variable BS should also be 0. If all states produced by one task having the unlimited storage capacity, the corresponding variable YS and BS should be enforced 0 on all units at any given points. There are two objectives involved in this work. The first one is to maximize the profit within the scheduling horizon. All variables concerning the time should be smaller than the time horizon. And the second is to minimize mix span. The output of the products should satisfy the customer demands. And the finish time of the last event point on all units should be smaller than the mix span. Next, we address several benchmark examples using the proposed formulation to test its performance. In the first example, 3 instances with different time horizon are solved to maximize the profit. The computational results are compared with a literature work referred as V and S. The results show that the computational time is significantly reduced with the maximum reduction of 94%. This is mainly because the number of primary variables and the model size are reduced in our formulation, and the tightening constraints are introduced to improve the computational performance. In the example 2 and 3, our model uses 5 and 10 event points respectively to reach the optimality. But the literature model V and S should be with delta n equal to 1 and delta n equal to 7. Here the parameter delta n means the number of event points over which tasks can span.
Hello, Dan. Can you wind up in 2 minutes?
Sorry?
It's already time. Can you wind up in 2 minutes?
Oh, okay. Thanks. This means using the proposed model, all tasks don't need to scan over the multiple event points. And the example 4 has the large capacity. From the result, we can find that the model arm obtained better optimal solutions, and the maximum improvement is 5%. Finally, we can make the conclusion. An effective mathematical formulation is proposed, and it has good performance on both computational efficiency and the solution accuracy. And in next step, we would try to extend the current model to the problems with changeover and due date. And we also would like to try to integrate the proposed model into the decomposition framework. That's all about my presentation. Thanks for your attention and welcome to any questions.
Thank you, Dan. So is there any question to Dan?
Yeah, very nice talk. I have one related to that consumption in the production. You have shown that consumption is more than the production, right?
Yeah.
I think the consumption term is not a good term. You can use that demand. Consumption is not possible, no, without production.
Sorry?
It's shown in your study that consumption is more than the production.
I think no. The objective is to minimize the makes fun and also to maximize the production, and they are separate or optimized.
I think terminus correction is required. I think in place of consumption, you can use demand term.
We can use the demand. If we-
Demand.
yes, in the model, we also use the demand.
Okay, that's
Yeah, thank you.
So Dan, I have just one question for you.
Yeah.
So how you have fixed your event points?
The event point and is a parameter. I need to use the iterative process to determine it. So the result I have present here is I have used the best result of the event point.
Okay.
So I need to determine it before I run the formulation. It's just a parameter.
Okay, and the other model which you have compared with V and S, that is also event based?
The as you mean the literature work?
Yes.
Yeah. We use the totally same parameter, the same event point and the same objectives and so on.
Okay, all right.
Yeah.
Thank you. Is there any question to Dan? So if there is no question, let us thank our speaker.
Thank you.
Thank you so much, Dan.